Hello everyone, I'm Suzette Corbito and I will be discussing the application of calculus in traffic flow analysis. So I will start with the introduction, the definition, the diagram, and the sample problem. So for the introduction, 2 weeks ago while contemplating on my way home experiencing the congestion at Chauvel, I remembered the number one issue that my country, the Philippines, also faces, and it is traffic. So, according to statistics, the Philippines has a traffic index of 187.3 compared to Canada, which is 143.91. So, the traffic index is the percentage of additional time a road trip takes due to congestion. And then we know that calculus is an essential tool in many fields of science and engineering, including traffic engineering. So, traffic engineering involves the planning, design, and management of transportation systems. So, one part of it is traffic flow analysis. And calculus is a valuable tool for analyzing traffic flow, as it helps describe the changes in these variables over time and space. Usually, differential equations and integration can be used to model complex traffic scenarios. However, for this discussion, I will only show the basic equations for traffic flow analysis. So these are used by engineers to make better decisions to improve traffic flow, safety, and overall transportation efficiency, and better understand the traffic patterns, congestion, and how various factors affect traffic behavior. So we are given by the fundamental diagram of traffic flow, which is Q is equal to T times V, where Q is the traffic flow with the unit of vehicles per hour, and traffic density with vehicles per miles, and traffic speed, which is miles per hour. So the traffic flow is the rate at which vehicles pass a given point on the road. To simply put it, it is the number of vehicles passing through a reference point on the road per unit of time. And we have density, which is the number of vehicles per unit length of the road. And we have two densities, the critical density and the jam density. So these two densities will be given or discussed more on the next slide. And we have the traffic speed, which is the average speed of vehicles on the road. So we have the linear speed density relationship formula, which is the speed of traffic at a given density is equal to the free flow minus k times d. So the free flow velocity, it is the average speed that a vehicle would travel if there were no congestion. And this parameter, it would be determined from empirical data and field studies. And this jam density, it is the maximum traffic density at which a traffic can still flow but at a minimum speed. So we have the graph for this one as it shows the relationship of the two. To summarize this graph, it only says that as the traffic density approaches zero, so the speed approaches the maximum flow speed, which is the free flow. And as the traffic density approaches its maximum capacity, the speed decreases and eventually reaching it to zero, which we call the jam density. And we can correlate this relationship with the traffic flow analysis through differentiation. So assuming this is the traffic flow in relation to the traffic density and this is their slope. So the rate of change of the traffic flow with respect to the certain variable and the rate of change of traffic density or its slope is equal or is the same with the slope and its derivative. And we can also have the maximum traffic flow on this side based on this graph. So to simply put it out, the slope or the change in traffic flow over the change in density, that is its derivative, that is its slope. So we have the sample problem to understand it better. So you are a traffic engineering student major and was tasked with analyzing the traffic flow through Shawville, Southeast. Suppose we have the following information about the section of the road. So we have the speed density relationship, which is 60 minus 0.2 d. So this equation was derived from the linear speed density relationship a while ago. So this is one. So which is VO is the 60, which is from the Calgary speed limit map for that area, and K, which is 0.2, which is an assumed value because it can only be observed or get through studies and other empirical data. And the road has a length of 0.09 miles. And assuming that 5 vehicles pass through with that road, the initial traffic density at one end of the road is 56 vehicles per mile. So this 56 vehicles per mile was calculated by dividing the number of vehicles passing through that road, which is 5 over 0.09 miles. So this is the 56. So we will then solve for the traffic flow. And we all know that traffic flow is traffic density times traffic speed. And we will substitute the given speed density relationship. So we have d times 60 minus 0.2d. So by simplifying, we have 60d minus 0.2d squared. So this is our equation now, and we can get its derivative, or the change in free flow over change in density. So we will have now 60 minus 0.4d, and then we will substitute the d, to which it is 56 vehicles per mile. 60 minus 0.4 times 56, so we will get 37.6, or let's assume 38 vehicles per hour. So this is the traffic flow by using differentiation. And we have the part 2 of the problem, to which it is similar to applied optimization. With the same given, we will find the road's maximum capacity. So we all know that finding the maximum capacity means being the derivative to 0. So if 0 is equal to 60 minus 0.4d, then we will have the value of d, or the maximum traffic density, which is 150 vehicle per mile. And for checking, we can check it if the solved value is maximum or not by solving for the second derivative and substituting the value of d that we get in the first derivative. So the second derivative is negative 0.4, and since we get the negative value, which is to confirm that the 150 vehicle per mile is the maxima. So that is a basic example of application of calculus to traffic flow analysis. I hope you learned something with this presentation, and thank you for listening.